Alright. Again, Gauss's law, which you should all be able to recite by heart by now, is what we're going to work on, but it's on cylindrical. Geometry. Okay, so Gauss's law and cylindrical geometry is what we're going for here. Well, it was we had some good examples where, for example, for the sphere, if you have a point charge in the middle, it's gonna spread out on our Gaussian surface so that the field is uniform at all these at every place along the sphere. And that's really why we choose geometries, to make that situation happen. We want it to be uniform across the entire sphere so that we can go from E dot dA equals crank over epsilon naught to E times A equals crank times epsilon naught. That's our goal by choosing geometries, and we're just looking for a way to make this uniform across this area. With the point charges, it works nice for a sphere, but there are some situations where cylindrical is going to be the way to go. The first ones are ones where we have basically anything that's going to go out radially but not spread out in all directions equally. This was a sphere as I drew it. But what happens if instead I have a line of charge? These are all positive. Well, from one direction, like if I look at it straight on with the wire facing me, let's say that the current is going, or say the charge is inside here. Well, in this case, it's going to be uniform in all directions. This is the side view. But that view doesn't hold everywhere. That's the problem with it, is that it doesn't hold if we look at it from the front. From the front, it just looks like this line. So the best way to solve that, if we have two dimensions that are going to spread out evenly, and one dimension that's going to be just that's going to not spread out, that's going to be constant. In other words, if we look in two dimensions, in other words, the dimensions that are perpendicular to the wire or to the line of charges, in this case, E is going to be proportional to 1 over R squared. It's going to be proportional to 1 over R or something like that. It's going to be, in other words, it's going to get smaller as you go away. But in one dimension, parallel to the wire or to the line of charge, E is going to be constant. It won't matter where I choose. In other words, if I find the field here, it's going to be the same as the field here. It's going to be the same as the field here, because I didn't change how far away I was from it, and I didn't change where I was with respect to the line. Like moving from side to side isn't going to make me any closer to the line, so there won't be any shifting. The only way we can deal with that properly is to use a Gaussian surface that is a cylinder. to make E constant across the area, we're going to use a cylinder as the Gaussian surface. I guess one thing I would like to have done was to make a more compelling case. Let's say that we use the Gaussian sphere for this. Well, if it was a sphere in the direction that is, let's say we use a sphere for this part of it, or we grid the whole thing with a wire. In the direction this way, it would be constant. But in this direction, it wouldn't be constant because this part's closer, this part's farther, this part's the farthest away. So I wouldn't be able to turn my integral of E dot dA into just E times A. That's the big advantage of using this cylinder as a Gaussian surface. So if we take our line of charge and instead we wrap, this is the, let's make this the axis, it's going to be the center of it, and we put a Gaussian, we put a cylinder over it. Well, that actually turns out not to be terrible. Let's say that this line, that blank for the entire line equals Q. Okay, positive Q. Well, that means that we have, in our cylinder, we've captured positive Q over epsilon naught equals E times area. But our area is going to be kind of interesting because it's going to be the surface area of a cylinder, which is just the circumference times the length. So, and we know we're going to say the length of the wire is L. So in this case it would be E times 2 pi R L equals positive Q over epsilon naught. Our electric field is going to be Q over 2 pi epsilon naught RL. And a lot of these, and let's take a look at this. This makes sense if we have a longer wire for the same amount of charge. It's going to be distributed more. Like, let's say that Q over L is big, then that's going to mean we have a wire that's like charges are all compacted together. If Q over L is small, then we're going to have a wire that has space between them. That's all we mean by that. Okay. And you can see we got 2 pi epsilon naught, that's like half our normal constant. And R, as we get farther away from the cylinder with respect to the far away from the line of charge, we're going to get a smaller field, which we like. Another way that's common to express this is to say you have a line with a linear charge density. Which means that now you have a line here, and we know that it's going to have so many, it's going to have X number of coulombs per meter. So this is like a second case of the same thing. Well, we take our wire, or our line of charge, I should say. We make our Gaussian You'll note this time they give us this thing here, but they don't tell us how long it is. So we're going to make an arbitrary length L. And this time we're going to go back to, again, I hate to keep writing this, but I really want you to be in the habit of writing it every time. So we're going to have E dot dA equals Planck over epsilon naught, which again, E times A, sorry, is going to equal Planck times epsilon naught. In this case, to get Planck, we're going to have to take our linear charge density times our arbitrary length L. So this becomes lambda L for epsilon naught, and E, when we got a cylinder, is going to be 2 pi r L. The L's divide away, and our electric field becomes lambda over 2 pi epsilon naught r. Or if you're a big fan of the K constant, it would just be 2 lambda, or sorry, 2 lambda K over R. Either way is fine. It doesn't make a difference. But you can see that this is a little more, this is an easier way to do it, because now we don't have to care about how long the wire is. And technically it could be an infinite wire. I mean, like really, really long compared to its width is probably the best way to put it. It doesn't make any difference. Let's look at 2 more examples before I let you loose, or your sub lets you loose, or whomever is doing the loose letting provides that function. We're looking at, let's say we look at a hollow cylinder. So we have a cylinder that looks like this. With a surface charge density. And that surface charge density, the units for that are going to be coulombs per square meter. And it's going to be per square meter across here. So if I grab some little section of area, that's going to have a certain amount of coulombs in it. It's going to have that many coulombs per meter squared. Which means that in order to find out what Planck is, I'm going to have to sum all the way across this cylinder. Call this example 3. And this thing here is going to be, like I said, we'll give it a length L. Okay. And let's go ahead and see what happens. Because Planck, which is usually the trick to these things, is going to be the surface charge density times the surface area. So, if we're, let's give it a radius of, I don't know, B or something like that. From 0 to B, Planck is going to be 0, because we're going to have, basically we're going to have no charge inside. However, if we have a radius that's bigger than B, Planck isn't going to be 0. It's going to be equal to this surface charge density times the surface area of the cylinder, which is going to be 2 pi, not r, it's going to be b, because remember that's going to be the actual number. Times L. Remember, this is actually fixed. That's the actual amount of charge. Even if we make a Gaussian cylinder that's bigger, we're still only capturing the amount of charge that's actually on, it's actually on the surface here. We can't making a bigger cylinder isn't going to let us capture more charge. So we're going to end up with yeah, you're breaking my heart. And we're going to have EA equals Planck dot epsilon naught, since E is uniform across A. And it's going to be 2 pi BL over epsilon naught. And this is going to be E, again, it's going to be a cylinder of 2 pi R. Now, remember, we're allowed to have that. 2 pi L divides out. We end up with E equals B over R epsilon naught. And that sort of makes sense, that we're going to have this, what we forgot, this thing. That sort of makes sense. At R equals B, E is going to be just the surface charge density over epsilon naught. And as R becomes greater than B, E is going to approach 0, because this will get bigger and bigger and bigger. We'll eventually divide this puppy away, getting it close to 0. That's a good one. The last one I want to talk about is an insulating sphere. Or, sorry, cylinder. With a volume charge density. Yeah, I know, it's not fun. And we're going to call the volume charge density something. Let's see. We'll call it beta. Why, I don't know. But that means that beta is going to be coulombs per meters cubed. So again, we'll make it a radius of, we'll make a radius of A this time. And if we look, and again, the volume charge density is beta all the way through. Well, this time from 0, from when the radius is between 0 and A, Planck is not 0. But R equals 0, Planck is 0. Because we don't have any stuff to move, you know what I mean? That we haven't grabbed any of it yet. But it's going to be a little bit more complicated deal. And let's give it a length L. That'll be fun. It may not even matter. Let's see. So, as we do that, it's kind of like the volume density of the sphere. Planck is going to equal the density times the captured volume. So in this case, it's going to be beta, or from 0 to R to A, it's going to be pi R squared L. And we're dealing with the volume, not the surface area now. So E, okay. Yeah, see, I forget too sometimes. I don't want to write it either. But here we are, peeps. So, we have beta times pi R squared L over epsilon naught. Again, it's going to be E times A, because the field is going to be uniform across the surface that we chose, our Gaussian cylinder. It's going to be 2 pi R L. Well, the L's go away. That's nifty. The pi's go away. And we have E equals beta R squared over... Oh, I'm sorry, one of the R's goes away, doesn't it? So it's just... Oh, let's see if we can erase that. Oh, I love that. Okay, over 2 epsilon naught. Now I want to point out that that's good for the region 0 to R to A. Notice we're capturing more and more of the volume. So it's gonna. So as we capture more and more, we should get a bigger field. Even though we got a bigger space, we're capturing way more charge. We're capturing it, proportional to R cubed instead of just proportional to R. But where our surface area is increasing by R squared, so it should make some. It should increase by R. But how about when R is greater than B? Or sorry, A. That's what we chose. Well, we run across a limit because all the charge, crank, is just going to be the charge of the cylinder, which is no longer going to grow as we make larger Gaussian cylinders around it. It's just going to be beta times pi A squared L, which means that when we find our Gaussian surface, notice I write the little circle, that's just telling me it's a closed integral around the path. It's crank over epsilon naught. Again, E is uniform over the Gaussian surface. So that means that EA equals crank over epsilon naught, which is going to be E is 2 pi RL, or this is R because we are changing this. We're using whatever arbitrary size of Gaussian surface we want. This is going to be beta pi A squared L over epsilon naught. Notice some of our dividing stops. Well, actually our dividing of the radii stops. Our L's divide out, pi's divide out, and we have E equals beta A squared over 2 R epsilon naught. Now we're getting further away. Basically, it's becoming a line charge, or a wire that has a charge on it. As you get farther away, it should get closer and closer to 0, which is exactly what one might expect. Cool. Well, like I said, I will deliver a video about flat sheets, but I'm not going to do it now. I'll have to do it later. So, smell you later, everybody.